All right, hello. I'm gonna have to redo 3.6 here. The last video had audio issues in that there was no audio, so sorry about that, and hopefully get this video out here pretty fast for you. So basically what we've got here is we want to be able to take the derivative of more complicated functions, and this is a very big step towards doing that. Basically what the chain rule is going to allow us to do is to differentiate composite functions. Okay, I remember spending time on those, hopefully back in previous math for you in pre-calculus and everything like that. But basically the idea is if you have a function that's inside of another function, or you can break it into two functions, a function of a function, that we can use this chain rule. So if we look at this, when we took derivatives, if we took a derivative of y with respect to x, it would be dy dx. And I told you before that this was an algebraic structure. So just like up here, if I had something like 3/5, I could make this equal to 3 over something times something over 5. And as long as the number that I put here and the number that I put there were the same number, then this would still be equal. So for example, I could make this 3/7 times 7/5. The sevens would ultimately cancel, and you're still left with that 3/5. So I can do something kind of similar here. I can make this dy over something times that same thing over dx, and we'll make it a du, okay? And so we're introducing a new variable u here, and basically what we have here is we're going to have, so we'll have this be true where y becomes, so y was a function of x, but we're going to make a substitution, and we're going to make y a function of u, a new variable u, and u, this new variable, is a function of x. Okay, and when we do this, this chain rule will hold to be true. So let's try showing you this just in practice. That's usually the best way to get kind of good at this. And so we'll try this one here. Here we've got the function y equals the quantity 3x squared plus 1, and then that whole quantity is squared. And it's a composite of two functions. The first function, y, would be u squared, and the second function would be u equals 3x squared plus 1. So if you were to take this 3x squared plus 1, have it equal to u, and substitute that in for u squared, you'd get back this original function. Okay? And so that's the thing we want to do, is we're going to want to do it that way. So let's take a look here. What you would normally do, if you were doing this out long ways, you'd say something like let u equal, and then you want to pick the inside function. Remember doing this kind of stuff in pre-calculus where you were given a function and you had to come up with an inner function and an outer function, an f of x and a g of x that would composite together to make it. We're doing that same sort of thing here. Just, instead of writing g of x, we're writing u. And so then this y would then become, if we substituted out every 3x squared plus 1 with a u, this would become u squared, just like that. Now we need to take the derivative of each one of them. So this would be du dx, and the derivative there would be derivative with respect to x. So you bring the 2 out front, that becomes a 6x. The derivative constant is 0, so just 6x. And then the derivative of y with respect to u, dy du, is just going to be 2u. Right? There you go. So now we have what we need to put this together. So we look at up above here, this, right? And we say dy du is equal to, dy dx. Dy dx is equal to dy du times du dx. And so we just substitute those in. Dy du, that's right here, is just 2u. Du dx, right there, is just 6x. Okay? And then now we have it as a function of u and x, but u is a function of x, which means we can actually just take and substitute using this right here to get rid of the u. This would be 2 times u, which is 3x squared plus 1, times 6x. Okay? And now all we have to do is combine all that together, multiply everything together, and we'd get 2 times 3 is 6, right? And then 6 times 6 is going to be 36x cubed, because we had a 2 times the 3x squared times 6x. And then we have 2 times 1 times 6x. So that's 2 times 6x, 12x. And there's your answer right there. Now, the other thing you could have done to actually do this one, and it won't always be an option when we have these composite functions, but in this one, you could have expanded this out. You could have squared the whole thing out, had like a 9x to the 4th and stuff like that, and gone through and done it out as we would have done any polynomial before using just the power rules. And I actually would encourage you to go try that and see that you get the same answer as we got here. All right, it will work out to be the same, and you can go try that for yourself if you want to see it, just to kind of prove it to yourself. All right, so doing it this way, I really like this way, and it helps sometimes if it gets more complicated to write it out in this long way. But there's also just something else you can kind of do that's a little shortcut. And it's essentially, it is the chain rule, but we're just going to kind of do this. We're going to inside outside it. Essentially what we're going to do is do the derivative of the outer function times the derivative of the inner function, and keep the inner function plugged into the derivative of the outer function. All right? So if that doesn't make much sense to you, let's take a look here and let's try this. We're going to try a few of these and leave some of these for yourself to try, and then you can take a look in the notes and see. So let's start with this first one. Y equals the quantity 2x plus 1 to the 5th power. So the outer function, we're just going to do it this way. So normally what we would do is, pick an inner function and outer function, set it equal to u, do all that stuff, and go through and do it. But what we're going to do is we're going to do the derivative of the outer part. So we're just going to do this all like in one step here. That's 5 times 2x plus 1. So you have to be able to identify the outer part. That's the outer part. Times the derivative of what's on the inside. And the inside is the 2x plus 1, which is what we would have made equal to u. Times the derivative of 2x plus 1, which is just 2. And so ultimately, y prime equals 10 times 2x plus 1, quantity to the 4th power. Okay? And so that does it. That's it right there. All right? And if you want to compare, we could do an or, right? Or you could have done it the other way, where we would have said, let u equal 2x plus 1, and then du dx would have been 2, and we could say then that y equals u to the 5th, and dy du is equal to 5u to the 4th, and then dy dx, which is, that's y prime, is going to equal dy du du dx, which is going to be dy du is 5u to the 4th times du dx, which is 2. This is 10u to the 4th, but we don't want to leave it as u, and u equals 2x plus 1 right there. So we substitute, and this is 10 times 2x plus 1 to the 4th. So we get the same answer, you see? But that's because what we ended up doing was, this was the derivative of the outer part, and this was the derivative of the inner part, and then we put them back together. So this is the derivative of the outer, this is the derivative of the inner, and that's essentially what we just did here real quick. We just didn't write it all out. All right, so feel free to start doing them more this way and see how it goes for you. All right, I'm going to leave some of these for you to try. Keep in mind, right here, I'll give you a little hint. This is 3x squared minus 4x plus 6 to the 1/2. Don't forget that that's a 1/2. And I'm going to go down here and I'm going to try doing one of the trigonometric ones for you. Because, I mean, like with this one, if you were really pressed to try and do it, you could expand that out 9 times. It'd be really difficult, but I guess you don't have to necessarily use chain rule, but definitely for these trigonometric ones, you're going to have to use it. So let's take a look at this one. Secant of the tangent of x. Now we could go through and say, let u equal tangent x, and let y equal secant of u, and then do all that stuff. Or we can do derivative of the outer times the derivative of what's on the inside. Okay? So let's try that one. So the derivative of what's on the outside, well, the outer function is secant. So y prime is going to be derivative of secant, right, is secant, derivative of secant is secant tangent. So this is going to be secant of tangent of x times tangent of tangent of x, okay, times the derivative of what's on the inside. Well, what the inside is tangent of x, so the derivative of tangent, right, is just secant squared. Just like that. Okay? And that's it. So be careful with this. Don't think that this is secant times tangent times tangent times tangent, right? This is the secant of tangent. So the tangent is inside the secant. It's not secant times tangent. So you wouldn't want to turn that into something like tangent cubed times secant cubed, you know. Excuse me, that would not be correct. So don't do that. All right, so I'm going to leave the rest of the ones on this page for you to try. Take a look in the notes after you've tried them to see, see how they worked out for you. Okay, next. Same thing here. Actually, I may just go ahead and do one of these. This is exponential. So this is e to the negative fifth. So we do the derivative of what's on the outside times the derivative of what's on the inside. So, not too difficult there. So if you wanted to, you could do let u equal negative 5x, and then y is e to the u, and do all that. Or you can do derivative on the outside times derivative of what's on the inside. So we do the derivative of the outer function, which is e, the exponential, e, and so derivative of e to the x is just e to the x. So we just leave e to the negative 5x, and then do times the derivative of negative 5x, which is just negative 5. And so ultimately this is negative 5 times e to the negative 5x. Okay, and I'm going to show you it one more time with an or, just so you can see. Or you let u equal negative 5x, and then du dx is negative 5. There's that negative 5 that we got right here. And then we say y equals e to the u, and so dy du is just e to the u, and so dy dx, which is our y prime, is dy du dx, and dy du is e to the u times du dx, which is negative 5. So this is negative 5 e to the u, and remember, u is negative 5x, so negative 5x. So right there, we got this answer here doing derivative of outer times the derivative of the inner, and then we got it by doing the whole chain rule out. So, I recommend, again, practice both ways and make sure that you get to be pretty okay with it. All right? So on some of these things, it might be necessary to apply multiple rules here where you have to do more than just do multiple chain rules or do the product rule inside the chain rule or something like that. So that's what these ones here are practicing, is kind of putting all your rules together. So let's take a look at this one here. We've got sine squared of pi t minus 2. So if you look at this, we actually have something that's really more like this. We're doing the derivative of sine of pi t minus 2, right, squared. So when we see this like this, we actually have an outer function with the squared, then inside that is a sine, but then inside that again is a pi t minus 2. So we have like a function inside of a function inside of a function, which means you have to kind of double chain rule it. All right, so what we can do is we can just do that inner times outer thing. And so we'll do the outer derivative first, which is 2 times, and then we just leave in there what goes there, just like that. And then that's just to the first power now. All right, 2 sine pi t. Then we have to do times the derivative of what's on the inside. So times the derivative of sine of pi t minus 2. And so now we just have to work on this sine of pi t minus 2. So the derivative of that, you have to chain rule it. You have an outer function sine and an inner function pi t minus 2. So derivative of sine is cosine pi t minus 2 times the derivative of what's on the inside, the pi t minus 2. Well, derivative of pi t is just it's just pi, and then derivative of minus 2 is just 0, so it goes away. So this is just 2 sine, I'll bring this part down here, pi t minus 2 times that. And so this is what we have, 2 pi times sine of pi t minus 2 times the cosine of pi t minus 2. And there's your answer. Okay. If you wanted to try doing this, I'm not going to fully write it out, but if you wanted to try doing this with the dy, du, dy, dt's, that kind of notation, you would do something like u equals sine of pi t minus 2, and then you could say p equals pi t minus 2, like that. And then if pi t minus 2 is p, this becomes sine of p, and then y is just going to equal u squared. Okay, see if you can figure out how I just did that. And in that case, you would then go through, you'd have to do the derivatives of each one of these, do the derivatives, and then dy dt is going to equal dy du, du dp, dp dt. All right, so this one would be du dp, this one would be dp dt, and this one would be dy du. So you'd find each one of those, plug them in, start substituting until you got all the way back to only having t's in it, and you'd be done. All right, so if you want to give that one a try, it might be good practice for you. All right, everything else after this is just stuff I want you to try, and then check the notes and see where I put all the answers and see if it helps you. And if you have any issues with it still, contact me about it. But give these a try. The last couple pages, just some practice ones, and then check out the notes for it. This is not the longest section, but it is a kind of tricky one. So be sure you spend some time practicing on this one. It's something that's going to be used quite a lot going forward in the rest of this class. And of course, also quite a lot going forward if you continue on in calculus, or if you're ever having to do this in any of your science classes where you have to take derivatives. Sometimes you have to do that to get information from data you've gathered and stuff like that. So be sure you get this down as best as you possibly can. All right, that is all. Thank you.